Okay, Assalamualaikum and hi everyone. So we are waiting for our speaker for today, Dr. Paklen. Okay ke? Dah ready ke?
Wait lah. 1 minute juga, 1 minute.
Oh, tengah ready. Okay. Alright, while waiting for our speaker, so welcome to the SCCE Research Seminar Knowledge Sharing Webinar Series 6 to everyone. So before we start, there are a few announcements for the audience. Thank you for coming. And could you please fill in the two forms? The first one is the registration form. You may find the link at the chat box and the chat room. And the second one will be the evaluation form, but this form will be given at the end of our session letter. So you also can find the slide presentation and you can download them from the link given in the chat room. Okay, our speaker is ready.
Okay.
Okay, all right. So before we start, let me just introduce you to the speaker. And the title of our webinar for today is Hardware Implementation of Hybrid Multilayer Perceptron Neural Network. And the name of our speaker for today is Associate Professor TS Dr. PHAKLEN EHKAN. So before we start, I will be reading the speaker's biography for you to get to know his background first. All right, Associate Professor TS Dr. PHAKLEN EHKAN received a Bachelor of Engineering in Electrical Electronic Engineering from UTM, a Masters of Science in Information Technology from UUM, and a PhD in Computer Engineering from UNIMAP with joint venture with University of Birmingham in UK. Previously, he worked as senior engineer in multinational companies, which are in electronic industries for 6 years before joining the University Malaysia Perlis as a lecturer in January 2003. Currently, he is an associate professor attached to the School of Computer and Communication Engineering, and his research interests include reconfigurable computing and FPGA, digital design and embedded system, digital and image processing, system on chip, smart system, and IoT. He also has published over 90 articles in international journals and Scopus Index proceeding. So, Dr. PHAKLEN EHKAN is currently a chartered engineer, professional technologist with MBOT, a graduate member of BEM, and a member of IEEE, BCS, and IEC SIT. Is also actively involved in reviewing papers from established journals, including IEEE SS, Journal of Supercomputing, and lecture notes from Springer. Besides, he also involved in providing talk, and end of last year, he was appointed as keynote speaker at the 2019 International Conference Humanity and Technology in Egypt, and recently was appointed as guest editor in special issue on social impacts of big data applications, IoT and challenges, Journal of AI Society, and Knowledge, Culture and Communication Springer. So that's the biography of our speaker for today. So now, without further ado, let us welcome our speaker, Associate Professor TS Dr. PHAKLEN EHKAN, to give his talk on hardware implementation of hybrid multilayer perceptron neural network. So the board is yours, Dr. PHAKLEN.
Thank you, Dr. Fpga. All right, again, thank you again, Dr. Rafika, as a chair for today. All right, a very good afternoon to all of you. So today I'm going to present my students' PhD work entitled Hardware Implementation of a Hybrid Multi-Layer Perceptron Neural Network. So these are the outline of my sharing info for today. So we start with the introduction, followed by highlighted related issues on Hmlp, and followed by objective until the end of the end with the conclusions. All right. Okay. Hmlp is a start of artificial neural network ANN that is based on the multi-layered perceptron neural network. So the figure shows here the topology of an MLP with one hidden layer. So the input values are fed into the network through input layer and produce the output values from the output layer. So there is a hidden layer here in between input and output layer. So the Hmlp was proposed by Mashur in year 2000 by modifying MLP. So this is to enhance the performance of the MLP in modeling linear system by adding extra weight links that directly connected the input layer to the output layer, as you can see here, as can be seen in red dotted line here. So bypassing the hidden layer. So Hmlp is a parallel system which alike to most of the ANN because of each Hmlp is functional independently. So this is the output equation, and the red section here refer to the additional weight links. Okay, the training of Hmlp involve recursive adjustment to the values of the weight and bias of Hmlp. So modify recursive prediction error, or we call it in short MRPE, was introduced together with Hmlp to train the Hmlp. All right. So MRPE is a sequential, but because of update of the MRPE parameters such as theta t, here you can see some parameters here. So some of them depending on their previous values. That's why we call it MRPE is a sequential algorithm. So to the Hmlp is a parallel system, while the MRP is a sequential. Okay, so ANN's parallelism can only be harnessed by using a parallel system. So most of the existing hardware Hmlp was on sequential microcontroller. So therefore, a new concurrent FPGA based architecture of Hmlp is proposed to handle this issue. So no one size fit all Hmlp structure exists. So the Ni, Nh, and as well as the No parameters of Hmlp vary depending on applications. So scalable in the sense that the Ni, Nh, and No of Hmlp can be easily modified. And this will make the FPGA implementation of Hmlp applicable to different applications. Okay, different activation function may apply to Hmlp. So different approach to implement an activation function on FPGA may be developed. So modular design or modular architecture will help shorten overall development time, as different modules can be developed and validated separately. So as stated earlier, the Hmlp is parallel system, while MRPE or modify a recursive prediction error is sequential. So sequential MRPE will not benefit from implementation of concurrent FPGA. So SOC FPGA that has both concurrent FPGA, has both features of concurrent FPGA and sequential SOC, is on the same device. So Hmlp, MLP and Resilient BP was implemented on Xilinx platform before, but there is no report on ANN plus plus training implementation on Altera SoC FPGA was highlighted. So this implementation require new FPGA to SoC interface module for the target Cyclone 5 SoC. So with the issues or problem highlighted or in mind that I highlighted from issue 1 to issue 4 before, so the object we can set the objective of this work to develop and validate a Hmlp MRPE system implemented on SoC FPGA. So this include design concurrent FPGA based architecture of HLP, and we add the scalability and modularity, and as well as the design FPGA HPS interface module for the target SoC FPGA device. So this is the objective. We have three main keyword here. We are going to develop new concurrent, scalability, as well as the modularity. So why FPGA is chosen? So FPGA, as we know, that is known as a flexible and concurrent platform, hardware platform that is useful for prototyping of the digital system designs and implementation of concurrent architecture. So the concurrent of FPGA stems from its internal hardware component that is a content of a large amount of configurable logic block, or we call it a CLB, input-output blocks, IOB, and programmable switches and interconnects, which is in here. If you can see the figure in here is blue in color, interconnection switches. So the way this internal component of FPGA is arranged in a grid like pattern to create the FPGA fabric. So the organization of FPGA, internal FPGA's internal reconfigurable components permit the FPGA to implement multiple independent systems on FPGA fabric at the same time. So the internal hardware structure of FPGA also make the FPGA a very large general purpose logic circuit that can be easily reconfigured to implement desired desired digital system design, making the FPGA a practical platform, hardware platform to test and validate new digital system design. Guy, are you with me, Guy?
Yes, yes, you are here.
Okay. The SoC FPGA is a device that has two main components. So, namely, FPGA portion here, and typically an ARM-based SoC here. Sometimes we call it SoC, sometimes HPS. I will explain later why we call it HPS / SoC here. So the FPGA is a general purpose device that is capable to implement concurrent system. The SoC is like a microcontroller. It's based on a CPU that execute instructions in sequential manner. SoC FPGA device also is suitable to implement system which has both concurrent and sequential subsystem. So this figure, so the portion of HPS SoC in gray color and FPGA portion in light blue color. So there is a HPS dash FPGA interface here. All right, to interfacing between SoC and FPGA. Sorry. Okay. So Intel FPGA or FPGA in Intel formerly from Altera used the term HPS. HPS stands for hardware processor system. Actually, this to refer to the SoC of the SoC FPGA. So later on, I will use HPS and an SoC interchangeably. Okay, meaning that SoC actually refer to HPS. HPS is referred to SoC. It's same meaning. So these are the scope that of this work. So the target SoC FPGA hardware is the E1 SoC because of the E1 SoC have more logic element and better SoC spec compared to Xilinx Z board. Okay, and the architecture for the Hmlp is described using VHDL. So in this case, we use VHDL language in quarters 2, and floating point arithmetic IP are used to implement all arithmetic operation in Hmlp. The the FPGA to SoC interface module is described by using a QC's tool of quarters 2, and the MRPE training algorithm is programmed in C, in its program, or is coded in C for execution on the target of ARM Cortex A9 SoC. So on the validation parts, okay, on the validating part, so validation of FPGA-based architecture of Hmlp is done by comparing the outputs from FPGA to the outputs from Hmlp implemented on MATLAB and Hmlp implemented on SoC only. So validation of Hmlp MRPE system on SoC FPGA is done by training the Hmlp MRPE to deduce the output of 4 input XOR operation. So this deduction of XOR output is one of the test method used to verify the basic functionality of ANN and its training algorithm. According to few articles that we have gone through. All right. So the outputs of Hmlp MRP on SOC is compared to the outputs from Hmlp MRP implementation on MATLAB, and so basically we compare with MATLAB. Okay. So this list here are the existing hardware implementation of Hmlp. So the amount of available onboard memory, you can see here, this is the Hmlp, and this is a platform used for implementation, Hmlp implementation, and then this is the application of the Hmlp. So they apply in cervical cancer classification system, and they got one paper in 2012 for InnoSat attitude how to say control simulator. All right. So the amount we can from here we can conclude that the amount of available onboard memory is the main limitation of microcontroller based implementation of Hmlp, and you know, the RC M4100, so running at 58.98 megahertz with 512K flash and memory, 256K, I think data of SRAM also facing more or less the same problem. All right, this is the this slide shows the top level overview of Hmlp MRP. So on the left is the FPGA. This part used for Hmlp architecture, and on the right is a SOC, ARM Cortex-9 SOC, used for the MRPE training algorithm function. So there is an interface here. Okay. So for the development of FPGA-based Hmlp module, the hierarchy of Hmlp FPGA module is shown here. So this is the figure of the Hmlp. So this is the top level of the Hmlp top level module. So we have hidden layer module here. So inside here we have hidden node module, few of them, and output layers module. We have output node module and few of them. So this is the diagram of the Hmlp. So floating points number repeat, you can see here, right? So is it continuing from previous slide? So we use the floating point number representation in this design, which we call it a standardized data format for easy interfacing of data between different type of device. So we have HID underscore MADD and also our underscore MADD modules. So these one are very familiar. So only multiply add module at output node has extra extra node here. If you can see extra here, compared to here. So they have one extra with VLIK and also VOI. All right. Also only one FP multiplier and also one FP floating point adder IP module to reduce the resources utilization. So this important for the scalability. So input data are pipeline in FP floating point multiplier and also floating point how to say adder. This is to reduce the processing time. So this is this slide show the function, the A function underscores. Okay, this signal has 4 operations here. So negation by inverting the sign bit, floating point exponential, floating point addition, and also floating point inverse. All right. So we have 3 here. So only how to say, only A function linear has the h, how to say, finite state machine for control signal. So the higher level modules mainly function to instantiate submodules and route the signal to appropriate submodule. All right. So this is the hidden node module. This is all top level, and this is and on the right hand side is output node module. Okay. Oh, this is the higher level of the Hmlp FPGA. All right. Like I say just now, top level module mainly function to instantiate submodules and route signal to appropriate module. Okay. So once finish the development phase, so we continue with the validation. All right. So the Hmlp FPGA module is then validated. So the validation mode include the validation include the basic functionality, verify the correctness of the computations, comparing its implementation on different platform, compare some parameters like in here. So we have done at this phase. All right, this slide shows the simulation of Hmlp underscore FPGA module using simulation test bench on Modelsim. All right, this is the one. And on your right hand side is the implementation of Hmlp underscore FPGA module using synthesizable test bench on Cyclone 5 SoC on board D1 SoC. All right. So we can see if they produce more or less the same number. All right. So the above table here shows the FPGA resources utilization of Hmlp underscore FPGA module. So this include the synthesizable test bench. This one for Hmlp with Ni equal to 2, Nh equal to 2, and N equal to 1. So we occupy a lot of how to say adaptive logic memory in here. All right, and use of 5,531 of register, 35 of DSP block, and so on. So this is the FPGA resources utilized by the Hmlp underscore FPGA module. So this one is this slide show the comparison. All right, Hmlp executed on MATLAB and Hmlp implemented on HPS of the E1 SoC. Remember, HPS actually refer to SOC. So this one actually same, how to say this, sequential. Yeah, it's sequential. So you can see they produce the same number. All right, same values here. So except the processing time, of course, Hmlp processing time on Hmlp slightly higher, or we can say slower than Hmlp processing times on the HPS. So this the table here show the comparisons parameters we values and output latency from Cyclone 5 SOC, Modelsim, MATLAB, and HPS only. Okay, as can be seen here, all output values are very similar, with only minor differences with at the end least significant bit. These differences not really affected the hardware implementation. So this occur basically is due to the underlying hardware. So this one we consider as a normal issues. Or this slide shared how the overall output latency of Hmlp _ FPGA module is carried out. So you can. Okay, this is the top one, the blue in color, is a hidden node processing time in here, and then bottom one is output node processing time. So there is a plenty of time here. Wait for hidden node done signal, meaning that before carry on this process, this one got to wait for hit nodes done signal here. So that means we only can start from this point. All right. So the overall output latency of Hmlp FPGA module would be 73 plus 7 Ni plus with a 7 H. All right. 7 refer to 7 cycles. All right. So this graph shows the output latency. All right, output latency of the Hmlp of varying the how to say I think Ni here implemented on different platform. So we have Modelsim, we have DE1 SoC with different clock cycle. One is 50 megahertz and the other one is 100 megahertz, and also the Modelsim 100 megahertz clock, and test bench for DE1 SoC using 100 megahertz clock. All right. So the increase of number of input nodes will increase the latency, you can see here. Same goes to NH, all right, and then NO. And then this slide show the modularity of Hmlp _ FPGA module. So wearing activation function module. All right. So this is the how to say the programming or the language for the hidden node, and this one for the output nodes. All right. This is the module of them. This is for the hidden. This is for the produce the from this program we did to produce this Hmlp output nodes. All right. So this figure shows the development of remember we have we have HPS, then we have FPGA, right? So we need interfacing module in order for them to communicate to each other. So this figure shows the development of FPGA and dash HPS interface module. So we use how to say, this module is described using a QS tool, Quarters tool. It used as a bridge for the Hmlp underscore FPGA module to HPS. All right. The figure here shows the process flow of the FPGA-HPS hardware processor system interface module. So in here we use a C language. C language application is coded and cross compile for execution on Linux to operating system. It's running on the ARM-based HPS. All right, you can see this is the blue box here refer to Hmlp operation. So this is the process of the Hmlp operations. In this slide, the table shows that the resources used for top-level module, user I/O module, Hmlp FPGA, and also the FPGA-HPS interface module. So a significant amount of resources used for FPGA-HPS interface and module. This might limit the size of our Hmlp underscore FPGA module to be implemented. All right. So this one we need to consider how to reduce this usage. So from this slide, you can see that the parameters of V, all right, the parameters of V for HPGA-HPS and synthesizable test bench are the same. All right, are the same. So meaning that here, all right, the value are the same. So this show that the data passing between HPS and Hmlp underscore FPGA modules are correct. So yeah, because of you can see the same number here. All right. This is show here is as setting for ni equal to 2, nh equal to 2, and n equal to 1. So this is the way the values of the parameter values of the network. Yeah. So as I said earlier, the Hmlp is developed on FPGA, while MRPE training algorithm function is done on ARM Cortex. All right. So the integration between these two is interfaced by FPGA SoC interface. Sorry. This is the interface here. All right. Interface module that we also developed this one. So the Hmlp dash MRPE system to be implemented on DE1SO is validated first by training the Hmlp FPGA module to deduce the output of 4-input XOR operation, as I mentioned just now. So how the XOR operation works? The output you can see here, if there is a pair for the 0 and 1, the output will be 0. If you have odd number of 1 or odd number of 0, the output will be 1. You can see here we have 3 zeros, 1, and you have 1. So 3 zeros, 1, only 1, 1. So we have a couple of zeros and a couple of 1. So the output is 0. So we use this for input XOR operation to deduce to validate. So the graph here, all right, the graph here determines the which Hmlp structure has faster conversion. So in here we use MSE is applied for the MSE stand for mean squared error. So it's applied for the purpose. So the smaller values resulting less error. So all right. So if you look at here, we have a big value here. So it's going down. So at NH2 equal to 2 and NH equal to 3 will not converge to an acceptable values even after training. But when NH equal to 6 converge, fastest at about 10 epoch. So in here. All right. So meaning that the MSE values is almost 0 here. So it shows that very less error. So in this slide, the table shows the FPGA resources utilization of Hmlp-MRP system on DE1 SoC for Hmlp with different NH. All right. So Ni we set to 4, N0 is set to 1. So we increase the NH 4 to 5 and 5 to 6. So this is all right. And then the FPGA resources utilization of Hmlp underscore FPGA module increase with larger, you see, all increase with larger Hmlp structure. So larger Hmlp structure also will increase the FPGA resources utilization of the FPGA HPS interface module due to more weight and bias that need to be connected to HPS. Okay, so meaning that the circuit will become complex. This is the comparison the Hmlp-MRP system implemented on DE1 SoC to Hmlp-MRP system implemented on MATLAB and also on the HPS. All right. So also using I mentioned just now, using 4 input XOR deduction. You can see here, I don't know whether you can see clearly or not, there is an error here. All right, but the error is towards, you can say that 0. So we have 16 combination here, XOR, and then this is out. This is what we expected. Like I mentioned earlier, if you have a pair of input bits, so the output should be 0. So expected output should be 0. If you have a single one and 3, let's say 3 zeros here, the output should be 1. So this is what we get, and this is what expected. So this is the error, MSE. All right, means error. Okay, this is on D1 SoC. This is on MATLAB, and this is on HPS only. Oh. Okay, so comparing the Hmlp-MRP system implemented on DE1 SoC to Hmlp-MRP system implemented on MATLAB and on HPS only. All right. Maybe you cannot see. Actually, we indicate with red color here, FPGA plus HPS implementation on DE1 SoC, and we have blue color MATLAB implementation on computer, and then we have a slightly black color on the HPS only implementation on D1 SoC. All right. So all of them, you can see here, all of them, we can say that it produce very similar result. Okay. So as the conclusion, we propose, develop, and validate a new approach to implement the Hmlp and MRP on SoC FPGA device. So the new approach, we call it a new concurrent, scalable, modular SoC FPGA-based architecture on Hmlp implementation. So this is like proper name. We call it proper name of this development. All right. So this the concurrent FPGA-based architecture of Hmlp implemented on FPGA at clock frequency of 50 megahertz. This clock able to compute its output at shorter time than Hmlp implemented on SoC only, from Ni equal to 5 and H equal to 3, or N O equal to 2 onwards. All right. And FPGA-HPS interface modules to connect, between FPGA-based Hmlp module and to the HPS module was developed. So this module is able to pass data between the HPS and the Hmlp on FPGA with correct data integrity. The Hmlp MRP PE training, a system implemented on the Cyclone 5 SoC FPGA, it's also is able to learn to deduce the output of 4-input XOR operation. So as the how to say, the contribution of the works, I can say that we introduced the new approach to implement the Hmlp neural network and also MRP training algorithm on hardware, especially the Cyclone 5 SoC FPGA device, and a new FPGA-based architecture for implementing the Hmlp neural network on FPGA was proposed with a design characteristic of a concurrent, modular, as well as the scalability. And then the last one is we also managed or successfully or designed the FPGA HPS interface module. For the future works, we still can see the loophole for this work. So for the future work, probably we need to implement the sigmoid activation function using different approach. We list here some of the approach. So, and second one, to use different HPS to FPGA bridge to pass data between Hmlp on FPGA and also MRPA on HPS. This is to improve the how to say, the passing, to reduce the passing time of the data to FPGA, between FPGA and how to say, HPS. And the third one, to execute different training algorithm on HPS. We're working on the MRPE. Probably you can try on WRLS, MRLS, LM, and so on. You remember just now when I list out the application, one of the InnoSat one, they use WRLS for the training algorithm. Okay. To the fourth one, to implement, of course, to implement HMLP-MRE system on other SoC FPGA device. Higher end SoC FPGA device will have more FPGA resources, as well as the performance of it. So allowing the implementation of large HMLP, not probably we can have more nodes and probably more hidden layer, and with a shorter processing time. All right. So with that, I think, yeah, I come to the end now. So I pass back to the chair.
All right, Dr. PHAKLEN, thank you very much. Well, I must say that that is a very interesting and very nice presentation. However, it's a very detailed and technical as well. So involving the topic of FPGA and neural network. Okay, HMLP is actually a hybrid one from a basic MLP neural network. So, but we also know that both field actually involving FPGA and artificial intelligence is among the trending research topic nowadays. So, so for the students, you might want to consider this as a research topic for you. And so now, so I open the floor for any question that you want to ask to Associate Professor Dr. PHAKLEN. If there's any, you can turn on your mic or maybe you can type on the chat box. Okay, there's one question here from Dr. Noramina. Why do we call FPGA as hardware implementation, Dr. PHAKLEN?
Because it is not software. No. Okay. Okay. The reason we call it, my title is hardware implementation, right? So you asked me why FPGA is called hardware, right? So FPGA basically is a hardware. Hardware actually is a hardware circuit that a user can program to carry out one or more logical operations. So furthermore, FPGAs are the ICs or integrated circuits, which are set of a circuit on a chip that is the array part. If you remember, you can see the how to say the C of the CLB just now. And then with this FPGA, actually there is no chip. The user can program the hardware circuit or circuits on it. That's why we call it FPGA as a hardware.
All right. Okay.
I don't know whether you all get get the answer or not. Hopefully, yeah.
Yeah, hopefully that answered the question for Dr. Noramina. Anyone else want to ask any question? You may also ask basic questions, if this field is actually new, because I know that sometimes FPGA is rarely being used for some people, as opposed to like basic microcontroller, maybe Arduino, Raspberry Pi, right? So you might also want to ask basic questions on the why FPGA and what is the FPGA potential. Maybe you want to know about that. Or maybe you Dr. Butler want to answer that question.
Okay, Dr. PHAKLEN,
Yeah.
I would like to ask a question.
Yeah.
I'm Dr. Muhammad Sharaza from UNIMAP. I'm not in this field. I just want to clear up my mind. Actually, FPGA, is it something like a motherboard in a computer?
No,
Something like that, or
it's different. This is like I mentioned just now. This is the chip with a how to say, like empty chip.
or something like microcontroller?
It's something like microcontroller, but they have the FPGA they have extra features like compared to microcontroller. So they have like you heard about parallelism and pipelining kind of things. So we can apply this idea on the FPGA. So normally microcontroller you work in sequential. So if let's say I go like this. If let's say you want to add the number 1, 2, 3, and 4. All right, you want to add these 4 numbers. If sequential means you have to add one by one. You have to add 1 plus 2 first, then you get 3. Then 3 plus 3, you get how? You get 6, right? Then 6 plus 4, you get 10. So you need at least 3 clock cycles in order to complete the addition process. In FPGA, this is a just simple example. In FPGA, probably you can do 1 plus 2 and 3 plus 4 at the same time. 1 clock cycle, you do both. 1 plus 2, and then 3 plus 4. Another clock cycle, you add up the answer from those 2, and you get 10. So you save 1 clock cycle.
Oh, that's mean the FPGA something like a board that has a extra circuitry in that board.
No, actually the board is empty. You can program anything. Yeah, you can program the board. In fact, you can apply in any field. You can apply in communication field. You can apply in many fields. Yeah. Normally we use FPGA for prototyping. Some people ask, what after you finish prototyping, what's next?
Okay, that's mean it's handle the digital signal only, not the analog signal.
Digital signal that you can convert the analog to digital, right?
Oh, also can.
Can.
Okay. Clear. Thank you very much.
No problem.
Dr. PHAKLEN.
My dear.
Thank you, Dr. Shari. That's a very interesting question. For the beginner, maybe you really want to know why FPGA, what is FPGA as opposed to the basic microcontroller, right? So any other question maybe?
Dr. Paklen.
Yeah, Dr.
Yeah,
Paklen.
Yeah, Imran.
Yeah.
Yeah, thanks Paklen sharing with us. Okay, well, just want to ask you, if you compare the performance of the algorithm implemented in FPGA compare with MATLAB, what is the advantage of FPGA?
Oh, just now,
Uh-huh.
I didn't mention about the spec of the computer
Yes.
running on MATLAB, right? So okay. So you ask what is the performance, right?
The performance, maybe the FPGA is better, right, compared to MATLAB. So, any idea? Because just now you see you compare, you show the results, you run in MATLAB and also the results with FPGA. So, anything you want to say?
So I didn't share with you all with the concept of a pipelining and parallelism actually in this project. Yeah. So the concept is, like I mentioned just now, Dr. Sharazil just now, you can do something in parallel, which is you don't depend on the previous value, then you can go ahead with the how to say, with the that operation. So probably you can, you have to look in many angles to improve the how to say, to the operation. Some of them you can do in parallel. No need to wait for one finish, then do two finish, do three, something like that.
Yes, right. Yeah. So in MATLAB it is sequential, right? But in FPGA we can do in parallel.
Yes.
Okay. Thanks. Very clear. Thanks.
All right, no problem.
Thank you, PM Dr. Imran, for the question. So we have another question here from our chat room from Dr. Rosalita. With a lot of microcontroller option, why do we choose FPGA, Dr. Paklen?
This question you ask FPGA people. So normally FPGA people say FPGA.
Bias, eh?
Yes. So I don't know whether the microcontroller you can do reconfigurable. I mean reconfigure the things.
So maybe you want to explain more why. What is meant by reconfigurable?
Long story.
Okay. In short.
The microcontroller, normally microcontroller is there. So you just I think when you develop any project on microcontroller, you don't. I believe most of the people, they don't think about how to go for, how to say, parallelism, parallel and pipelining kind of thing. So they just develop the system and let it run. If they got the answer, they don't bother about how to say, about the
Performance.
how to say, about the method probably. Yeah, for us, we consider which one we can make it run in parallel. Very hard to answer. Then we try to, because we are dealing with the cycle time, we are dealing with the how to say, clock cycle kind of thing. So I don't know about microcontroller. I think they don't bother about this, right? As long as they can run the project on microcontroller, they are okay.
Maybe when it comes to commercialization, then you need something beyond that. So
Actually, there are pros and cons actually here.
Okay, I hope the answer that answer Dr. Rosalita's question. Okay, there's one more question here from Andisa Putra Utama. Dr. Paklen, can AFGA, is it? AFGA?
No, FPGA actually said.
Oh, FPGA. Okay,
I don't know.
FPGA be simulated in programming software? I think it's FPGA. Can we simulate it in programming software?
What I don't know whether what is FPGA. I believe this is FPGA.
I believe he meant to say FPGA.
If actually we have a soft computing also on FPGA. Andy, we can do that.
So what kind of programming software that you can suggest actually to simulate the FPGA design?
Good afternoon, Doctor.
Yes, Andy.
Good afternoon, Doctor.
Yes, Andy. Yeah.
Dr. Paklen.
Yeah.
Yes, silakan.
Sila.
Okay, Doctor. Long time no see.
Yeah, yeah.
Saya nak tanya ini doktor.
Dr. Padang,
Untuk ask
kita
you,
boleh tutup dulu presentation tu.
Doctor, I want to ask about the method of FPGA. Can you simulate it by the software like a simulation how FPGA works?
Simulation, how FPGA works.
How your method that you have developed is working?
There is a procedure how to simulate on FPGA. FPGA normally we use the famous one. We use Verilog or VHDL. Some people call it code. Some people call it language. But we use these two. But with the latest technology, there is a lot of how we can use QCs. We can a lot of features on FPGA now. But you're talking about language. Normally, this two is very famous, lah. Actually, we have handle C, we have C-based, we have handle C, we have they have C-based hardware programming C-based. Yes, they have also.
I mean, the priority is for the hardware, right? Not for the software, but it's for the embedded system.
Embedded system. What kind of embedded system? Are you refer to FPGA or you refer to other board like Raspberry, or you refer to Arduino, or you refer to other microcontrollers?
I mean that this method is really embedded to the Raspberry, something like that.
Yeah, yeah.
It is
no. Let's say we have one project you develop on the Raspberry Pi, right? So normally, you don't consider about how to say processing time, right? You don't really consider about optimization. Would be you just you just want to make sure that your project can run, then that's it.
This is for optimization, right? This is for to optimize that the runtime processing.
No,
That's
normally
to
people use
the speed.
FPGA for prototype. Let's say you develop one project or one system on FPGA, right? Let's say your project is running. So what to do next? So probably you go for you can think about how to enhance your system by optimize you can optimize the resources. You can optimize you can reduce the how to say processing time. You can do a lot of things on FPGA because this is prototype.
Okay, doctor. Thank you so much.
We can discuss further, Andy. Don't worry.
All right, does that answer the question, Andy?
Okay, it's enough.
Okay, thank you for the question. There's one more question here, Dr. PHAKLEN. How many layers are used in this proposed neural network? Just curious. How many layers are being used in the Hmlp NN just now?
Oh, I use only one layer for hidden.
One hidden layer.
Yeah. And then one more question is FPGA can be used to run multiple tasks at the same time without any delay.
Yeah, that's a compliment.
Yeah, actually it depends on what task you are doing. If the task is not interrelated to each other, then probably yes, you
not
can run.
Every task can be run in concurrent ways, right?
Yeah. Yep. It depends. Yeah.
Okay. All right. Any other question from the audience before we wrap up?
Hi, Dr. PHAKLEN.
Yeah.
Can I ask a question?
Yeah, please.
Faiz here.
Yep.
All right. So, can I know what is the actually simple question? What is the application of this algorithm?
What's the purpose
Which one?
of
Hmlp?
Yes, Hmlp.
No,
what is the application? The target application of it?
Actually, they got so many applications, but for us, we try to build the prototype. Like I mentioned just now, right? We try to build a platform for Hmlp. So this platform can apply in many applications. Let's say we go for modularity. So if let's say you want to develop the application, let's say big application, so you just probably change that module. And then we have one more, just now we call it the concurrent is one. And then we have a scalability. So by increasing the number, so we can we create the part by part for this.
Part by part, okay. I mean, it doesn't have any specific application. It's a general
Yes, yes. In
process,
general, yeah.
something like general processor that can be implemented other applications, something like that.
We don't go for specific application, but we just develop architecture for that.
Oh, okay. All right, thank you, Dr. Parallelism.
So later probably we can try work it out on use this how to say this model, try to apply in any application like you know, a few application in biomedic.
Okay.
Like I mentioned just now, yeah.
I believe this is the like extension of the basic MLP that we have already known. We have
Yes.
multilayer perceptron, the basic one. So this is the hybrid one, the more advanced one of MLP. So you can actually push any, I believe you can push any classification task to this particular architecture so that it can actually help to classify anything. All right, any other question from chat box? So far all question has been asked. From Facebook, are there any question, Dr. Nora? Can't see the Facebook. I hope there's no question over there.
No question from the Facebook.
All right.
Yeah,
thank
no
you, Dr.
question.
Azhar.
Yeah.
All right.
Okay, if there's no more question, then I have one last question. Okay, shall I ask Dr. Valen? So when you have actually designed everything, after you have successfully developed that on FPGA, so what's next? What do we do next? So
Oh,
and over there, yeah, what?
what to do next? Okay. If after, let's say this we have to test to make sure that the architecture is really work. So probably the next step is probably you can create like you can create the IP, or maybe you can create the system you pass to like micro E people so they can think about fabrication the system later.
Interesting.
That's right. Some people say, how about system on chip? Yeah.
Ah, okay.
Yeah,
So it's towards that,
Yep.
designing and then going towards the SOC.
Yep.
All right, thank you for the answer. So since there's no more question, I believe, so I think that's it for today. So to everyone, thank you very much for joining us today. Please do not forget to fill in the evaluation form. So I think you may find the link at the chat room. But before we end our webinar, maybe we can turn on your camera for a sweet group photo session maybe for everyone. Could you please turn on the camera? So Dr. Nuramina will help us in capturing the moment.
Are we ready?
Is everyone ready? Can everyone turn on the camera?
Okay. Okay, one.
Oh, angkat skip spek tu.
Okay, 1, 2,
Right.
3.
Okay.
Banyak
Then
guna,
Okay, can we have one more, please? Sorry.
one more. Okay, one more.
Okay, one more. All right. Okay, 1, 2, 3. Okay, thank you.
All right. Thank you everyone for joining, and maybe we can meet again in the next webinar session from SCCE maybe next week, right? All right.
Thank you all. Thank you for joining.
Okay, thank you, Dr. Paklen, for a very marvelous talk. All right.
All right. Bye.
Okay, bye. Assalamualaikum.